Welcome everyone. For today's prep video, we're going to see how to find the potential function for a conservative vector field. And so in class last time, we were looking at, if we had a vector field, we looked at a few different tests, ways to determine if a vector field was conservative or not. And now we're going to see how to actually figure out if it is conservative, how to figure out what that potential function is. And so we're going to look at a two-dimensional example for right now. So what we're after here is we want to find a scalar function little f such that the gradient of that function is equal to the vector field capital F. And the formula for our vector field here, the first component function is 3 plus 2xy. And the second component function for our vector field is x squared minus 3y squared. All right. So we're going to see how to actually do this. But first, again, it's helpful to remember what exactly is the gradient of a scalar function. So this is where we do the x partial of the function, and that's our first component. And then we do the y component of that function, y partial of that function, and that becomes the y component. So we end up with a vector here where the first component is the x partial and the y component is the y partial. All right, so what we want to do is, well, let's write out let's compare this with our vector field. So the idea is if this vector field is going to have a potential function, well then this first component, this 3 plus 2xy should be our x partial derivative. So what we're going to do is we're going to start with our x partial derivative, which in this case it should be 3 plus 2xy. And what we're going to do is we're going to integrate this with respect to x. So we want to undo that x derivative, so we're going to integrate this with respect to x. And when we do that, we're going to get our function little f. So let's do our partial integration, partial antiderivative. Antiderivative of 3 is going to be 3x. Antiderivative of 2xy is going to be x squared plus y, or x squared times y. And then the addition here just stays the addition. Now, normally when we integrate, we throw a plus c on at the end. Well, because we're doing a partial integration, we're integrating just with respect to x, rather than plus c, conceivably there could be y terms. So instead of plus c, we're going to write a function solely in terms of y. So this is kind of taking the place. This has the role of plus c back in Calc 1 when we first introduced antiderivatives. Normally we find the antiderivative function, we throw a plus c on at the end because when we differentiate a constant, it becomes 0. Well, in this case, rather than just plus c, when we do our x partial derivative, constant terms could have gotten canceled off because of differentiating constant, but any terms that only had y's in them also would have gotten canceled off. So these were the terms that were left over once we did our x derivative. So antiderivative of 3 gave us 3x, antiderivative of 2xy gave us x squared y, but then there might have been a whole bunch of other terms here in our original function that all would have differentiated to 0 because they didn't have an x in them. All right, so once we have this function all written out, we still need to figure out what this unknown function was. So what we're going to do is now we're going to look at the second component of our vector field, and that should be our y partial. All right, so what we're going to do is we're going to take what we have so far and we're going to differentiate with respect to y. So we're going to differentiate this with respect to y. And let's see what we get. So that's going to give us our y partial. Now the derivative of that 3x, there's no y there, so that's just going to become 0. The derivative, partial derivative of that x squared y is going to become x squared. And then these are all y terms. We don't know what they are, but when we do the partial derivative of that, it's just like doing the regular derivative because there's only y terms there. So we end up with the partial of these first parts gives us the x squared, and then we don't know what g of y, what this function g of y is, so we're just going to say the partial of that is g prime. All right. So this is what we get based on what we have so far for our function, but we also have this piece of our vector field. And if we set those equal, we get that f prime should be equal to x squared minus 3y squared. And so if we compare these two results, if we compare and essentially set them equal, we see that both of these have an x squared. And if we compare, we see that negative 3y squared should be equal to this unknown function g prime of y. So kind of set this term equal to this term, and then cancel off any common terms, and we get that g prime should be equal to negative 3y squared. And then from here, we're going to integrate with respect to y. So when we integrate this with respect to y, that's going to give us g of y. Antiderivative of this is negative y cubed. And because we've already gone through the x integration, there shouldn't be any x's here. So at best, the only thing that could have possibly gotten canceled off was a constant term. We've already taken care of the x's. Now we've taken care of the y terms. So the only thing that could have gotten canceled off from here with the derivative is a constant. So this tells us this unknown function g of y is negative y cubed plus some constant k. And so then we just update. And so our function, our scalar function f of xy, is we have this 3x plus x squared y. And then we also found what this function was, g of y. We just figured it out. So it was negative y cubed plus c. And you want to think of this potential function, what we're doing, this is kind of like an antiderivative. And so normally with antiderivatives, we have a plus c at the end, same kind of deal here. So what we're doing is essentially to find the potential function where we end up integrating each kind of piece of our vector field. We integrate the first piece with respect to x. We can integrate the second piece with respect to y. And then we just kind of compare everything to see what pieces got canceled off. And so normally we want to start this, just start with the x component, integrate with respect to x, get the function, plus some unknown terms. Differentiate this then with respect to y, and that'll tell you what the derivative of those unknown terms are. And then you can integrate and kind of keep working your way. So we're going to see an example like this in 3 dimensions. We're going to do it in class. But this one's just to kind of get things going here. All right, so this is the idea. And well, like I said, we're going to try a 3-dimensional case next time. So we'll see you then. Bye-bye.